Good afternoon, students. Welcome to the lecture of Operation Research. In the last lecture, we have started the new topic, quadratic programming problem. In this section, we have seen what is the quadratic form actually. Okay, the quadratic form of a given function in 2 dimensions we have seen, in 3 dimensions also. Okay, and then we have generalized it for a n-dimensional space. So for the quadratic form in every dimension space is of the form x transpose x. Okay, where x is the matrix of variables, rather it's a column vector, and that's why we were considering this to be x transpose x. In detail, I have told you how it is going to give us the quadratic equation in the variables. Say in this equation, it is a quadratic equation in 3 variables, say x1, x2, and x3. Therefore, in general, we have given the quadratic form in an n-dimensional spaces and is of the form x transpose qx, which is actually summation I from 1 to n, j from 1 to n, aij, xi, xj. Okay. Later we have seen without loss of generality that the matrix under the consideration A should be a symmetric matrix. I have told you the reason as well. Because if the matrix is given, it is easy for us to find out the quadratic form. But if the quadratic form is given, then if I am interested in finding the matrix, say, then we are giving equal weightage. See, in this example, whatever is the x1, x2, actually we are giving equal weightage to the variable x1, x2 and x2, x1. That is the coefficient a12 and a21 we are giving equal weightage, and actually it constructs the symmetric matrix. If the given matrix under the in the quadratic form is not symmetric, one can construct it with the symmetric form with the help of this formula, half a plus a transpose. Later we have seen one example of finding a quadratic form for the given matrix. We have found it. Then we have constructed the symmetric matrix corresponding to A, and later we have checked out the quadratic form, and we have observed both the quadratic forms are same. Both the quadratic forms are same. Then some properties of quadratic form we have seen: positive definite, positive semi-definite, negative semi-definite, and indefinite. In detail, we have discussed all the properties along with the examples as well. Then the general definition of a quadratic programming problem tells us that if x transpose and c belongs to Rn, okay, x is actually a column vector, that's why we were considering this to be transpose, so that it will be a row vector. So both this x transpose and c are the row vectors, are the members of Rn, means both are the n-tuple row vector. Then Q be a symmetric matrix of order n cross n, which is a real matrix. Then the problem of maximizing f of x equal to cx plus half x transpose qx. This is the objective function. If we look at this objective function consists of linear terms as well as the quadratic term. This half is just an adjustment. I will explain you this while explaining the Kuntakar conditions. Subject to the condition, say x is less than or equals to b and x is greater than or equals to 0. Therefore, general quadratic form or general quadratic programming problem is a programming problem in which the objective function is quadratic, but the constraint of the given programming problem are linear. This is what a general QPP is. Now in today's lecture, we were going to understand how the quadratic programming problem can be solved. For this, we are going to use a Lagrangian method, which is generally used for solving a nonlinear programming problem. As I told you already in the last lecture also, nonlinear programming problem is a programming problem which is not linear. What is linear? Linear programming problem is the programming problem in which objective function and constants both are in the linear form. Non-linear means there is no condition of linearity on the objective function and the constant. And whatever this quadratic programming problem we were going to study is a special case of non-linear programming problem in which objective function is not linear but the constraints are linear. Therefore, first we will study that Lagrangian method for constructing the necessary condition for the optimization of the given problem. Okay, let me start with Lagrangian method. This Lagrangian method is actually the Lagrange's method of multipliers, in which we were using the parameter lambda. I hope you have studied somewhere this in your graduation level itself. Okay, therefore we are going to study Lagrangian method. Okay, now this Lagrange's multiplier method gives us Lagrangian. This is called as multiplier method. Lagrange's multiplier method provides a necessary condition. Provides a necessary condition for optimization of the given programming problem. Necessary condition for the for an uh, optimum objective function when constraints are equation. Constraints are equations. Constants are equations means those are not given in the form of inequality. Or if they were given in the form of equality, we can convert it to equations by adding the suitable variable as we have discussed already. Now what we were going to consider in this Lagrangian function is of the form f of xy, and the assumption is this function is a differentiable function. Differentiable function and subject to the constraint g of xy is equals to 0. We will consider a particular case in terms of two variables. Later we will generalize this for in case of n variable. Okay. Therefore, what is the objective function under the consideration? F of xy. Now the function may be linear, may not be linear, but one should consider the function to be a differentiable function subject to the constraint g of xy is equal to 0. Okay, now with this is actually going to construct a non-linear programming problem. This is non-linear programming problem. Okay, because there is no restriction on the objective function and the constraints to be linear. So this is non-linear programming problem, and we were going to develop the method for non-linear, and then we will apply this to quadratic programming problem. Mathematician Kuhn and Tucker has used this method in order to construct the necessary condition for the quadratic programming problem that we will see in the next section. Okay, now this is the problem under the consideration now. Now what we were going to assume is, let the optimum of this function occurs at some point x naught y naught, at which this partial derivatives of g, dou g by dou x and dou g by dou y, does not vanish simultaneously. Okay, what we were going to assume, if g is also differentiable, because we were finding the derivatives of both the objective function and linear. Therefore, what we were going to assume, if an optimum occurs at a point say x naught y naught, at which at least one of the partial derivative, dou g by dou x or dou g by dou y does not vanish. Does not vanish means are not zero simultaneously. Okay, then we can proceed as. Follows. Okay, what we have assumed, optimum. We have assumed if such a optimum of this object programming problem occurs at the point x naught y naught, where at this point, dou g by dou x, dou g by dou y does not vanish simultaneously. In general, also, if I consider both the derivatives, dou g by dx and dou g by dou y 0, what will happen? G is the function of two variables x and y. If both the partial derivatives, dou g by dou x and dou g by dou y 0. What does it mean actually? Dou g by dou x is 0 means there is no x variable. Correct, na?
Yes, ma'am.
And dou g by dou y not equal to 0 means there is no y variable. And as such, there is no y variable, there is no x variable. The function is equated to 0 means it's a 0 function. What we were going to assume, at least one of the partial derivative at this point x naught y naught does not vanish, and then we can proceed as follows. Now at this point x naught y naught, we will going to consider that the curve g of xy is written in the form of explicit function, right? Let me write near x naught y naught, near x naught y naught, the equation of the curve g of xy equal to 0 can be written as, how can I write it? Say y equal to h of x. Okay. See, we have assumed dou g by dou x, dou g by dou y not equals to 0. One of them is not equals to 0. Which actually gives me the Jacobian matrix and non-zero Jacobian determinant. I hope you are remembering this concept we have studied in real analysis 1, implicit function theorem. What is the condition essential for the implicit function to write in the explicit form? Jacobian determinant is non-zero, correct now? And this whatever we were going to assume will assure that the Jacobian determinant is non-zero. Therefore, this implicit function we can write in the explicit form. Okay. Now, what we will do? We will now let us try to differentiate this g at the point x naught y naught. What will be a differentiation of this g of xy equal to 0? Let me call this to be equation number 1, and let this be equation number 2. What will be a differentiation of this g? Okay, 2 implies. Before differentiating, let me substitute the value of y as h of x. So g of xy equal to 0, can I write as g of x is equal to 0? Okay. Now let us get the derivative. Total derivative with respect to x, because it's the function in one variable only. What is the total derivative? May I write this is equal to 0 at x naught y naught? Right now. What is the derivative? Dear students, I hope I am clearly audible to everyone. Hello? Hello?
Yes, ma'am.
Audible, na?
Yes.
I'm worried actually if you are not giving me the answers. Okay. Is the derivative okay to everyone? Just I have found the derivative of this g. Dou g by dou x plus dou g by dou y into dh by, sorry, dh by dx it is. Na? Okay. Now what we will do? We will take the differentiation of 1 also. Now as we are considering the optimum occurs at the point x naught y naught, what is the first necessary condition for the optimization tells us? Is the first derivative of this function is 0 at the point x naught y naught, d by dx say. Right now? For extrema, first derivative of f is equated to 0. Okay, now let me find out the first derivative and let us equate it to 0. Therefore, let me write, since at x naught y naught what since x naught y naught gives the constrained optimum the constrained optimum value we have. What we have d by dx. Therefore, h again I will get h of x. What is derivative? Dou f by dou x at the point x naught y naught. Let me call this as statement number 4. Now let me use that Lagrange's multiplier method. Now I am going to introduce a parameter lambda such that, okay. Now out of the both has to be non-zero. Assuming dou g by dou y not equals to 0, let me define the Lagrange's parameter. Suppose dou g by dou y is not equals to 0 at x naught y naught, we can define a parameter lambda. We can define a parameter lambda by how I am going to define dou f by dou y minus lambda times dou g by dou y is equal to 0 at x naught y naught. Okay, I have taken the parameter lambda as such. Actually, this is giving me the value of lambda as. Thus, what will be a value of lambda from this equation? This is dou f by dou y upon dou g by dou y. And that's why we want this dou g by dou y to be non-zero, because it is going to appear in the denominator for the value of lambda. Is the point clear now? Since dou g by dou y is non-zero, we are going to define the parameter lambda with this equation. Now let me call this as statement number say 5. Okay. Now what the process we will do? We will multiply dou g by dou y minus lambda. Yeah. We will multiply this equation number 3 by lambda, and we will subtract it from 4. Okay. Dou f by dou y. Okay. What we will do now? Can I write the statement 3 minus what is dou g by dou y? G function equation number, yeah, it's 3. Oh, sorry, it is 4 minus 3 into lambda. 4 minus 3 into lambda. Okay. What it is going to give us? Look at this 4. 4 is dou f by dou x plus dou f by dou y into dh by dx. 3 is this. Now I am going to multiply 3 by lambda and subtract from 4. Therefore, the first term we will get is dou f by dou x minus lambda times dou g by dou x. Okay. Added with dou f. Now what we will do? We will take dh by dx common. Dh by dx common, and we will left with dou f by dou y minus lambda times dou g by dou y is equal to 0. Okay. Look at these equations again. This is 4. This is 3. We are going to multiply this 3 by lambda and we will subtract it. Okay. Therefore, first term is dou f by dou x minus lambda times dou g by dou x. Then we will take this dh by dx common. Then dou f by dou y minus lambda times dou g by dou y. I hope there is no difficulty. Okay. But we have defined a parameter lambda such that this term is 0. That is dou f by dou y minus lambda times dou g by dou y is 0 by equation number 5. Okay. But if this is so, what is going to result? What is the result of this equation then? Dou f by dou x minus lambda times dou g by dou x plus dh by dx into 0 is equals to 0, and this is at x naught Why not? Correct now? Therefore, may I say this gives me another equation dou f by dou x minus lambda times dou g by dou x is equal to 0 at the point x naught y naught. Okay. Therefore, this is the 5 equation dou f by dou y minus lambda times dou g by dou x, and whatever is this resultant, let me call it as number 6. Now look at the equations very carefully. Thus, we have equations. Okay, first equation we have is dou f by dou x minus lambda times dou g by dou x is equals to 0. Second equation is dou f by dou y minus lambda times dou g by dou y equal to 0, and this is no doubt at a point it's not random. Therefore, if I look at the equations carefully, may I see or may I construct, or rather Lagrangian has constructed a new functions. Okay, what Lagrangian has set up the new function L of x, y added with this parameter lambda, and he has defined the new function to be f of x y minus lambda times g of x y. Here we will write if we set. Actually, Lagrangian has set up this function, and this capital L is given in his honor, Lagrangian. L stands for Lagrangian. So he has defined a new function L of x y lambda is this. So looking at the two conditions, therefore what we can say from our equations, may I say the first one is dou L by dou x is equal to 0, and the second one is dou L by dou y is equal to 0. Correct now? If I differentiate this L with respect to x, what will be my term on the right? Dou f by dou x minus lambda times dou g by dou x, which is actually this term where it is equal to 0. If I differentiate with respect to y, this is dou f by dou y minus lambda times dou g by dou y, which gives me dou L by dou y is equals to 0. So whatever the two conditions we have obtained, okay, whatever the two conditions we have obtained, or one can say that and original constraint is obtained by was the original constant g of x y is equals to 0. Therefore, these are actually called as the end optima, which is actually our original objective function, and these conditions are equivalent to the optimization of the unconstrained objective function say here. Here there is no constraint now for this L.
Hello, ma'am.
Therefore, this is unconstrained problem. Therefore, these three conditions
Ma'am, you are not audible.
Hello,
Hello, ma'am.
am I audible, students? I think there was no network in between. Hello,
Hello, ma'am.
yes, hello, who is speaking?
मॅम तुमचा व्हॉइस मधून मधून ब्रेक होतोय.
Hmm.
स्क्रीन पण
Today I
स्टॉप
am
होते.
facing some internet issue. Here it was showing a message on my screen as well that your internet is not stable. Is the voice clear now? Should I
Yes, ma'am.
continue?
Okay, ma'am.
Okay. If it is going to give us a disturbance again, what we will do? We will stop and then we will go. We will take it in the next. Okay. Let me repeat again. The original constraint under the consideration, original problem under the consideration is a non-linear programming problem. F of x, y, a function in two variables, subject to the constraint g of x, y is equal to 0. Both are assumed to be the differentiable function. Now we will assume if the optimum of this programming problem occurs at some point, then at least one of the partial derivatives should not does not vanish. Okay, both of them cannot be zero simultaneously. Okay, then at this point x naught y naught, first we have written the implicit form of a function. First we have written the implicit form of function to explicit one, that is y equal to h of x. Then we have differentiated the function g. Okay, and this is equal to 0 at the point x naught y naught, no doubt. And what is the derivative of this g? Dou g by dou x, dou g by dou y into dou g by dou x. Later, if the function is having an extrema at the point x naught y naught, then we know the methodology, the necessary condition, that the first derivative of the function is equal to 0. Therefore, we have found the first derivative of our objective function f of x comma h of x, and we have equated to 0, and the value is dou f by dou x plus dou f by dou y into dh by dx is equal to 0. Now let me assume that dou g by dou y is not equals to 0, because we have assumed initially that both of them cannot be zero simultaneously. Then let us minus equation given to lambda, which resolves this equation. But already second bracket is 0, so automatically we will get this bracket 0. Thus, we have obtained two different equations, y minus lambda dou g by dou y is 0. Right? So what Lagrange thought of to construct a new function, and that's why he has given the notation for the function to be capital L, where L stands for Lagrangian, which involves three variables x, y, and lambda, say, and which is defined as f of xy minus lambda times g of xy. Looking at the two conditions, the partial derivatives of this L with respect to both the variables must be 0. Also, if we differentiate this L with respect to this lambda parameter, this gives me the original constant. Now, shall I write it here? Dou g by dou x is equal to 0, negative x, minus g of xy is equal to 0. Therefore, these three are actually the conditions, rather the necessary conditions for the optimization of this new function L. What this new function L is? This new function L is a problem of unconstrained. Correct. Therefore, this gives the necessary conditions for the unconstrained optimum function L. These are the conditions for unconstrained optimum function of this function L. Right. Now, the same are given to be the necessary conditions for the optimization of our constrained problem. What is my constrained problem? This is my constrained problem. Correct? No? This is the constrained optimum problem. Whatever the three conditions we have written as the necessary conditions for the optimization of the function L are equivalent to the necessary conditions of optimization of the original function. Right? Let me just write the statement. Thus, the necessary conditions for an unconstrained optimum of capital L. What are the conditions actually? Namely, vanishing of three partial derivatives of L. Three partial derivatives of L. Okay, these are also the necessary conditions for the unconstrained optimum of L are also necessary conditions for a constrained optimum. What is a constrained objective function now? Constrained of f of xy assumption dou g by dou x and dou g by dou y does not vanish at a point x naught y naught. Okay, the function L defined is called Lagrangian multiplier. Okay, now have you understood the subject to a constraint equation g of x y equal to 0. Now let us generalize this necessary condition for the optimization of the function of two variables to in case of n variables. Shall I proceed? Whether the voice is clearly audible? Hello? Hello? Am I audible, students? Hello?
Yes, ma'am.
Generalization of Lagrangian method. Now, what method we will follow simply in n-dimensional case if we have n variables, okay, subject to some m constraint. Now, as we have used one Lagrange's multiplier for one constraint in this case, what we will do, whatever the number of constraints we have, we will use that number of Lagrange's multipliers. Later, we will construct the Lagrangian and we will differentiate the Lagrangian function with respect to all the variables involved, and we will equate the partial derivatives to 0. And whatever the equations will be constructed are the necessary conditions for the optimization of the problem, or rather the necessary condition. Right? Suppose, let me consider the problem now. Suppose to find an optimum of a differentiable function z equal to f of capital X, which is actually f of say x1, x2 to xn, or one can write x is in Rn, right? Subject to constraints constants m less than or equals to n. What are the constant equation we were writing now? Gi of x is equal to 0 for I equals to 1 to n, and x is greater equal by 0. Therefore, here the constraints are in the form of equations, no doubt. Right now, where all these functions gi is also differentiable, where gi's are also differentiable. Now, what this previous method tells us, simply construct a Lagrangian. How to construct a Lagrangian? In one constraint case, we have defined a Lagrangian as O objective function minus Lagrange's multiplier into the constraint. Now, how many constraints do we have in this section? In all, m, no? Not m. M constraints I am going to consider. Therefore, for every constraint, we are going to use one Lagrange's multiplier. Therefore, how many Lagrange's multipliers we were using now? Lambda 1, lambda 2 to lambda m, right? And original variables, m Lagrange's multipliers. Therefore, the Lagrangian function is of n plus m variables total, right? Thus, now we form the Lagrangian function. How can I form the Lagrangian function? How many variables in all? Let me write it in terms of vectors. Therefore, may I write the Lagrangian function is in terms of vector x and lambda, where it is defined to be original objective function minus, okay, now what minus actually? Summation lambda I into gi of x, where I runs from 1 to m, okay, okay, where this vector lambda is a m tuple vector of all the Lagrange's multipliers. Therefore, how many variables we have in all? How many variables we have in this section? N original variables we have, right? And m Lagrange's multipliers we have. Therefore, the number of variables are m plus n. Therefore, now necessary conditions are constructed by differentiating this L with respect to each variable. So, there are in all m plus n equations. And there are in all m plus n equations. Right? The necessary conditions. Necessary conditions for maxima or minima of the system of m plus n equations. Okay. What are the first equation? First, we will differentiate this L with respect to original variables. What is original variable? Let me write xj. Therefore, is it dou L by dou xj? What will be the derivative? Is it dou F by dou xj minus? We have to differentiate this with respect to xj as well. What I will do, I will write L again and then we will do the differentiations. We write L of x and lambda is f of x minus summation I equals to 1 to m lambda I gi x. Good. Now what is dou L by dou xj? Gives us first equation is dou F by dou xj minus. Now this summation as it is, every equation, every constraint g must be differentiated with respect to x. So this is dou gi by dou xj I running from 1 to n. How many such this is equal to 0? No, no. How many such j is having the value 1 to n? N variables are there in all, right? No. Now let us differentiate this with respect to the Lagrange's multiplier. Therefore, let me write dou L by dou lambda I. What is dou L by dou lambda I? If you just observe this, what's the value? What is dou L by dou lambda I?
Minus gi of x.
Is it minus? Yes, this is minus gi of x is equal to 0. And the value is L of I is from 1 to m. For how many equations we have constructed in all? M plus n equation. And these are the necessary conditions for the optimization of L, which is the original objective function. For here we can write which we can solve. We can solve for m plus n unknowns. What are the m plus n unknowns? x1, x2 to xn and lambda 1, lambda 2 to lambda n. Right? So these are necessary conditions for the optimization of given programming problem. Okay, and lastly, we will just write one statement. Here we are saying the conditions are necessary only, but what for sufficient? Now, these necessary conditions become sufficient if the objective function is concave for maxima and convex for minimum. These necessary conditions also become sufficient for maximum into bracket minimum objective function if objective function is concave or for minima it is convex. Okay, and side constraints are equality. Okay, so today we have seen the necessary conditions for the problem or rather non-linear programming problem. Now this same methodology we are going to apply for our quadratic programming problem case. For our quadratic programming problem case. Okay. If there is no difficulty in my voice, if the voice is not breaking, shall I continue? Or shall I go for the next lecture? Kuntakar conditions. Today network is giving me some trouble. It is very big one actually, Kuntakar conditions, and network is not giving me nice support today. Right? So let me stop for today's lecture and I'll take the Kuntakar conditions for the Kuntakar conditions, which are actually the necessary conditions for the quadratic programming problem in the next lecture. After studying Kuntakar conditions, we will go for the first method of solving the quadratic programming problem, that is Wolf method. Let us stop for today. If you have any difficulty in this Lagrangian method, you can unmute yourself and ask. Yes, students, any difficulty in today's lecture? If not, let me stop for today. Thank you for being with me for this lecture.